So now I'll take my discussion forward and I will look at, okay, we implemented this with a D flip-flop. Now what do I do if I want to implement this with a JK flip-flop? Okay, so I am going to take out this entire thing and go to the next page here. Okay, I'll leave this here. It's the same state diagram, same sequence detector that we are talking about, but I just want to implement this using JK flip-flops, right? So there might be a scenario where a JK flip-flop is available, and if you want to basically go ahead and do this implementation using a JK flip-flop, right? If you want to do this implementation using JK flip-flops, you need to convert the JK flip-flop to a D flip-flop first, right? Or the advantage with doing it using JK flip-flop, you will see, is you can exploit certain Boolean simplifications from there, which I will highlight now, right? But in any case, as I told you, the flip-flop states and all that stuff is a hidden variable. We don't care. All we care is for the X and the Y, and when 3 in ones come, you want to see the output going high, otherwise it should not go high, right? That's the simplest requirement that we have. So therefore it doesn't matter if you are implementing it with a JK or a D or a T flip-flop, right? So let's now go and see what we need to change here. We are now talking about two. So the number of states are the same. So therefore we just need 2 flops, right? I can call it a flop, by the way, instead of a flip-flop. It's a slight tongue twister. So I will call this as A, B and JA and JAKA, JB and KB. Okay, essentially this is what we have. Flip-flop 1, flip-flop 2, right? So everything in this state table remains the same except what we want to give here. This is the only thing that is now going to change when we move from a D flip-flop to a JK flip-flop. Okay, so I will talk about flip-flop inputs here. Let me give myself a little more space. Yes. Okay. So I've got myself the space that I need. I will now talk about flop inputs. I need to know what my JA and KA are, JB and KB. Okay, and of course please keep in mind the JK flip-flop characteristic table. Qn plus 1. Okay, 0 0, it's just going to retain Qn. 0 1, it's going to reset. 1 0, it's going to set. 1 1, it's going to toggle the output. Okay, this is what is the characteristic table. So in order to now analyze the JK flip-flop, right, we need to look at the present state and the next state. Okay, in the D flip-flop case, it was very easy. The next state was just the input to the flop, so it was very easy for us. We had nothing to do there, right? So now what I'm going to do is I need to look at this row and this row, because I'm trying to figure out what JA and KA have to be. So if the present state is a 0 and the next state is a 0, right? So it turns out that J has to be 0 here, right? So maybe I'll use a different color now, 0, right? But KA, given that the present state is a 0, it's okay to either be in that same state or to reset the flop, right? Therefore, Ka can be anything. Whether it's 0 or 1, you see these two states, it doesn't matter, right? And therefore, I can put a don't care condition on my K map, something that was not possible in the D flip-flop case, right? Now, likewise, my present state is 0, again 0. So, again I would just simply do this, right? I am going to do 0 x here, okay? Now, for row 3, as usual, let me also number this so that 1, 2, 3, 4, 5, no, I think I will just call it 0 to 7. 1, 2, 3, yeah. So, row 0 and row 1 is very straightforward because there is no change in the thing or it is getting reset. Now, in the present state, row 2 again 0, 0, I can just leave that as 0x. Now, present state is 0, next state is a 1, right? That means I need to either, so present state is a 0 and the next state is a 1. So, again it could be any of this. So, J has to be 1, K can be anything, right? Now, row number 4, present state is a 1, next state is a 0, right? So, again you could end up toggling the bit, okay, right. So, let us look at it. So, in row number 4, present state is a 1, next state is a 0, okay. So, I am looking at this here, okay. So, present state is a 1, next state is a 0, then I am going to I need to either toggle the bit or I can reset it. So, K will be 1, but J can be anything, okay. So, this is, sorry. Yeah. So, now likewise for row 5, present state is 1, next state is 1. So, you either remain where you are, right, or you are going to set. So, we are looking at this combination, you either remain where you are, right. So, J again K has to be 0, J can be anything, right. And likewise, if you look at row 6, we are at present state is 1, next state is 0. So, you are either going to go to, you are going to have to toggle the bit, right, you are going to have to toggle the bit, or you have to reset it again, right. So, therefore, so K will be 1, J can be anything, right. And finally, for 1, 1, you are either going to remain where you are or you are going to set. So, therefore, you are in this condition, that is, right. So, effectively, this is the JA and KA implementation that we essentially want here, right. So, right. So, likewise, you have to do exactly the same thing now for the JB and KB as well, okay. So, for JB and KB, I now need to look at this, okay. So, if I am going 0, 0, okay, then the the input that I need actually is going to go for. So, if you look at this, you can write, yeah. So, one thing that is very useful to do in this case is to look at what is known as an excitation table. Excitation table is the opposite of a characteristic table, where we are talking about the current state, the next state, and what the input should be. Okay, we are doing the inverse problem. So if you want this to be the case, look at this 0 1 1 0 1 1, right? So the excitation table, you know, the analysis that we did previously, we had to look at the characteristic table and derive this excitation table each time. So instead of that, we are just going to write down this excitation table for the JK flip-flop first and just use these entries to populate what JB and KB should be, right? So if you look at it, we are talking about Qn going from Qn being 0, Qn plus 1 being 0. So again, you're in this condition. So which means J has to be 0, K can be anything, right? On the other hand, Qn is 0, Qn plus 1 is 1. So either you are setting the output, right? You are either setting the output or you're toggling the output, and therefore J has to be 1, K can be anything. Then you're doing the case for 1 0, where you're basically saying the output is going to 0 or you're toggling. So you're looking at this case, these two cases, and therefore the K has to be 1, J can be anything. And 1 1 case, when you're looking at 1 1 case, the output is either staying at 1, that is this case, or the output is being set, right? So therefore again K is 0 and this is X. This is what we have. So all we have to do now is to look at the present state and next state, right? We have to look at the present state and next state and just map it to this JK from here, right? So we are looking at row 0 for B, right? It is a 0 0 condition, so I will use this, okay, 0x, right? Next I am looking at 0 1, right? If I am talking of 0 1, I am looking at 1x, right? Then I am talking about 1 in row 2, 1 1, I mean 1 0, right? I am talking of 1 0, therefore it is this one that I am talking about. So it will be x 1, right? And likewise row 3, I am talking of 1 0. Again I am talking of 1 0, and therefore this will be the answer. 1 0, sorry, again row 4, I am looking at 0 0, right? 0 0 basically is 0x, and row 5 is again 0 1, okay, present state, next state 0 1, so I get 1x, and row 6 is 1 0, right? 1 0 is this, so it will be x 1, and row 7 is 1 1, will be this is x 0, exactly, right? So now what you have to do is, of course, the output y is not going to change, right? Because that is just the output of the flip-flop, right? We are just going to put an AND gate there and we'll get it to work. However, the J and K inputs will obviously have to be different, and you can solve for the K maps, you know, for each of these JA, KA, JB, KB, and get the outputs appropriately for all the cases, right? And then construct the circuit diagram. You can Boolean simplify and then construct the circuit diagram appropriately, right? So essentially this excitation table is a very good tool for you to get used to. So you write this and keep separately, get used to this for all 3 flip-flops and simply work with these in order to populate these flip-flop input columns.